Okay, so let me know if you guys can see the screen.
Yes.
Okay, all right. So the next topic, if you look at right, so we will talk about the power dissipation. Okay. Now, what I wanted to do is this power dissipation, right? So mainly, you should understand from a CMOS perspective. Okay. So what is CMOS? It is complementary metal oxide semiconductor. Okay, so what we will do is we'll just quickly go over and understand what are the different MOS families. Okay, now if you look at the MOS family, okay, there are different families. Say for example, pseudo NMOS, okay, pseudo NMOS, okay, and then there is something called a CMOS, and then there is something called a POS transistor, okay, and then we do have something called domino logic, okay, and there is a one more which we call it I'm not sure, uh, transmission gates.
Transmission gate, sir.
Yeah, right, TG, transmission gates logic. Okay, so there are different logic families. Now what is that it is going to be used, which is the one which we are using actually. Okay, so now ideally speaking, if you ask me, the digital chips, any kind of digital chips that we work on uses pretty much CMOS. Okay, and POS transistors we do use it in analog and AMS circuits. Okay, and so this transmission gate is used occasionally in the CMOS. Okay, and domino and all I have not seen anyone is kind of using it. So ideally you should know about your CMOS, and then your POS transistors is just a basic level is good enough, and then transmission gate is again just you would. Okay, so where do we use this transmission gate in our digital? Mainly when you design a flip flop. Okay, inside D flip flop you would see the transmission gates. Okay, now coming to the CMOS. Okay, so let's talk about POS transistors. Okay, now say for example, now this is 5 volt, okay, and say this is 5 volt and your VT is 0.7 volt. What would be your output here? What would be the output? So it is basically, we look at it as a kind of VDD minus VT. Okay, now it is going to be kind of 4.3. Okay, now so when we say a digital, right, say this is your VDD and say this is your VSS. Okay, now what is that we actually prefer the signal to be? So the signal to be exactly at VSS, it's starting from VSS, and then it is kind of reaching VDD, and it is kind of again whenever you kind of say a logic zero, it is kind of coming to this level. Okay, but if you use this NMOS, okay, now what will happen to your logic 1? The logic 1 will be stopped at this level 4.3. Okay, so it is not going to go and reach. Okay, so it is not going to go and reach exactly 5 volt. Okay, so now this is something that we call it like kind of, say, the pos transistors, we don't prefer using it in our digital chips. Okay, now, so there is a homework. Okay, and what would be your V out? That is your homework number 1. And say the second problem is, so what is your V out here? Okay, so these two are your homework. Try to spend some time and find it out what it is, and how it would be the values and all of that. Okay, now let's talk about something called CMOS. So remember, when we say CMOS, there is a both the transistors. So it is basically both PMOS plus NMOS. That is the meaning. Okay, and in this case, we have there are when we talk about CMOS, there is a pull up network and pull down network. Okay, now here if you look at, so now if you look at this particular circuit, so this is your PMOS section and this is your NMOS section. Okay, now when you see complementary MOS, what is it meaning? At any point of time, only one transistor would be active. Okay, at any point of time, only one transistor would be kind of active. Okay, now so how it is possible? Now in this case, so when you give zero, what happens? When you give zero, what happens? What happens to your PMOS?
CMOS conductor.
On. PMOS is on, and NMOS is
Off.
Off. Off.
okay. And then when you give 1, what happens?
PMOS off.
PMOS is off and NMOS is
On.
On.
on. Okay. Now this is how the circuit is basically operates. Okay. And now let's give 0 here. What happens? Let's give, so assuming your waveform, so your voltage ranges are 0 to 5 volt. Now, so when you give 0 here, what happens?
PMOS will be on.
So your PMOS is going to be on. So it is going to charge this cap. Okay. This is going to charge this cap. And I will explain you what is this cap meaning in a while. Okay. Now remember, when it is charging, it is going to charge up to VDD. Okay. It is going to charge up to VDD. Now, when this is kind of 1, okay, when this is kind of 1, okay, now in that case, the NMOS is going to discharge them to VSS level. Now, what is this meaning is, if you use PMOS, sorry, if you use this whole CMOS, when your input is 0, so this actually acts as a kind of inverter. Now, when you give input is 0, your output is kind of 1. Okay. Now, when you give 1, the output is kind of becoming 0. Okay. Now, do you see the waveform which is kind of, going full swing? Do you see the waveform that is kind of going full swing? Okay. Now, that is the advantage of you using CMOS. Okay. Shruti, you have raised your hand. What is your question?
Sorry, sir, by mistake they came with.
Oh, okay. All right. No worries. Okay, so now PMOS, when you use PMOS, your the output waveform goes the full swing, so 0 to 5 volt. That is the main requirement in case of your digital chips. Okay, so now what is this meaning? As I told you, right? So we either operated cutoff completely or saturation. So in case of digital chips, we prefer only cutoff and saturation, and analog guys usually prefer the active mode. Okay, that is a main thing. Now, coming back to the same thing, now what will happen if you interchange? So now what is this function? What is this function? When you give 0, what happens? PMOS
One.
turns on and your cap is getting charged. Now the output is 1. Now when you give 1, output is kind of discharged completely to ground potential. Now, what is this function?
Inverter.
Inverter.
Okay, it is kind of inverter. Now, so there is a, okay, let's do a quick class work. What will happen if you interchange these two? What will happen if you interchange this PMOS and NMOS? So NMOS is on the top and PMOS at the bottom. What will happen?
Sir, buffer is created, sir.
Okay, so the functionality is basically what you're saying is it's kind of buffer.
Buffer, sir.
Okay, and any other drawback?
I mean, weak load, sir. We
Big
have
buffer.
weak load with buffer. We see.
What is the meaning of weak load? So
I mean,
load is basically the cap that is kind of constant, right?
yes, sir.
So what do you mean by weak load?
Like it is not fully discharged or fully charged, sir.
It will be a weak buffer.
Okay, so There is a better word for
CMOS
that.
won't
So,
charge you.
okay, so let me give you here. So, in case of this, when you use PMOS on the top, okay, so remember this particular thing, PMOS gives you strong 1, okay, and weak 0, okay, and your NMOS gives you strong 0 and weak 1. So now in case of PMOS on the top and NMOS at the bottom, what is actually going to happen? PMOS on the top, which gives strong 1, and NMOS at the bottom, which gives strong 0. Okay, now when you interchange these two, okay, now this acts as a buffer, okay, and this is kind of weak drive. This is a kind of weak drive. So your output waveform will not go all the full swing. So it is kind of, see, so it is kind of like this. Okay, it will not go to, so it is kind of, it stops at zero point 0.7 volt, and it is kind of stops at here 4.3 volt. Okay, so this is something that, buffer, but this buffer we don't prefer using it in our design. So we don't prefer swapping PMOS with NMOS. I mean, the pull-up network always it should be PMOS, okay, and pull-down network it should be always NMOS, so that you will have both strong 1 and strong 0. Okay, any questions here? Okay, okay, all right. So now if you want to if you wanted to have a buffer, then how do we, what kind of, how do we design this buffer? That's your homework. I want a buffer with strong one, strong drive. Okay, so how do we do that? So that's your homework, and I want the answers to be, posted in the group tomorrow. Okay, now the next thing is, let's quickly go over transmission gate. Okay, so what is this transmission gate meaning? So it is basically, you have your NMOS and you have your PMOS, which is kind of say A, and say this is kind of A bar, and this is kind of say input, and say this is kind of output. Okay, now this again going to give you strong 1, because your PMOS is kind of, going to give you strong 1, and your NMOS again will give you strong 0. Okay, but what is the what is the disadvantage in this? What is the disadvantage of transmission gate? So the main disadvantage is if there is a spike, if there is any kind of spike here, that spike gets amplified bigger. So ideally what is meaning is there is no noise margin. So in the TG, no noise margin, no noise margin. Okay, That is a main disadvantage. We don't prefer it using in our regular circuit design. I mean, our regular cell design and etc. Only in flip flop we have to use it because of the structure. Uh, but other than that, we don't use anywhere the TGs. Okay, that is a main problem. No noise margin here, so any kind of noise that comes in, it's kind of gets propagated. Okay. Um, Moving on to the main topic, the CMOS power dissipation. So there are two types of power when it comes to CMOS power dissipation. The first one is basically we call it like kind of the static power. Okay, when you say static power, the transistor is in off condition, and then there is something called dynamic power, which is kind of the power that is consumed during the switching. Okay, so now when you so let me ask you a simple thing. Assuming so you have a TV in home, so you off it with the remote. Okay, so you're not watching, you off it with the remote. Now, so the TV is basically off, is in off condition. So do you think there is no power consumption? Do you think there is no power consumption?
No, sir, there will be.
Okay, why is it so?
Because some of the devices or the chips will be on.
Okay. Uh, okay, so let me ask you another one more thing. Now, say you have got your phone. Now you put it in your, you put the phone in aeroplane mode, and you keep it just on it and just keep it in ideal mode. So neither basically you're not using the phone, and there is no modem which is on, no Wi-Fi, nothing. Okay, so the battery would be as it is, or will there be a power consumption, or the battery would get drained?
Battery will drain, sir. I mean, there
Why?
is a consumption. In background, there should be some work is going on in the chip, sir.
Okay. Okay. Now, so remember when you say static power, though the transistor is said to be in off condition. Okay, so we have discussed, say, a kind of cross-sectional thing. Okay, now say in cutoff mode, there is no channel is kind of formed. That is what we discussed, correct? Now, if you look at, though there is no channel is formed, but there would be some kind of conduction. Okay, now say this is kind of P substrate. Okay, now this is kind of say N plus. Okay, and this is kind of N plus, which is kind of say drain, and then this is source, and say this is kind of gate. Okay, now if you look at this actually, so try to recollect what we discussed when we talked about diode. So okay, so there is a kind of diode which is kind of formed. So this is P type material and this kind of N type material. Okay, and there is no channel formed, but even though there is no channel formed here, there would be a small amount of leakage. Okay, there would be something called subthreshold conduction. Okay, there would be something called subthreshold conduction. Now that is something that we call it as a subthreshold leakage. So though we say ID is 0 in cutoff, but your ID will not be exactly 0. That is because of your leakage. So when you say leakage, so there is something called a subthreshold leakage, and there is something called reverse bias diode leakage. So now here, if you look at, right, so this diode, again we talked about forward bias and reverse bias, so that leakage also comes into picture. Okay, reverse bias diode leakage. Okay, and there are many more. Okay, so these are all kind of not really important, but at least these two, if you are able to answer, which would be good enough. Okay, so if you really wanted to learn what are the different components that is contributing to a leakage, you can just go through them. Okay, so when you say static power, it is mainly we call it when the transistor, the power which is kind of dissipated during the transistor off condition, when the transistor is in off condition. Okay, and the next thing, it is something that we call it as a, the next one is going to be say kind of dynamic power. So dynamic power is, say for example, now you have got your phone and you're playing say a high end game. Now what happens to your battery? It just drains much faster, correct? So now that is because there are, two types of power, when the transistor is switching. Now when you play a game, there are a lot of computation happens, and then charging and discharging happens, and etc. So the first component that comes into picture is basically switching power. Now if you look at, say this is your, say, inverter. Okay, now when you give zero, as I told you, so this is something we call it as a load cap. Now it is actually charging. Okay, it is kind of charging. Now when you give one, now this is kind of discharging the cap. Okay, the load cap is kind of, charging, and when it is one, and it is kind of discharging. Now whatever the power that consumed at the time of this, this actions, is called switching power. Now switching power is mainly due to charging and discharging of load capacitance. Okay, and when you play a game, okay, now your charging and discharging happens much faster and frequently. Okay, so that is the main reason where your power is getting kind of consumed. Now that is something that we call it as a switching power. Now the next thing is something that we call it as a short circuit power. Now what is this meaning of short circuit power? Say for example, now it is at zero, the input is at zero. Now it is kind of going to one. Okay, now during zero, what happens? PMOS is on.
Charging.
Okay, and NMOS is off. Okay, now during this time, when you say one, now what happens? PMOS is off. Okay, and NMOS is on. Now if you look at, the sequence is going to be, PMOS is actually when during this transition. So during this transition, what actually happens? Your PMOS, so during this time, so your PMOS is going from on to off. Okay, now NMOS is again going from off to on. Okay, now for a fraction of second, when this is from on to off and this is off to on, now for a fraction of second, there is a direct path between VDD and VSS. There is a direct path between VDD and VSS. Okay, now that particular thing that we call it, so during the, during this switching, okay, whatever the power that is getting kind of, transferred or probably consumed or dissipated, it is called short circuit power. It is called short circuit power. Okay, that is called short circuit power. Okay, so now what are all different powers that we discussed? One is P leakage. Okay, that is one type of power, and second is P short circuit. Now, what does this meaning is it's basically whatever the current that goes in at this time. So it is basically ISC, that is a short circuit current into okay your VDD, that is your short circuit power, and the third it is going to be your P switching. Okay, now this is basically alpha C V squared F. Okay, now here this is switching activity. Okay, now this is cap, your load cap. Okay, and this is your frequency, and this V squared is your supply voltage. V squared is your supply voltage. Okay, now what is the total power dissipation here? What is the total power dissipation here? So your dynamic power equal to your P short circuit power plus P switching. Okay, now your P total is equal to your P leakage plus your P dynamic. So that is how your power, the total power that is kind of consumed. Okay, any question here? Okay, is it clear? So this is one of the important topic. Wherever you go, you have to know. I mean, basically, you should know what are the different powers, and even if you look at the PPA, right? So the first thing is basically we look at power. So power performance area. So you should know what it is, and when you are working on say simple, right? I mean, when you are working on a mobile chip, your static power is important. Okay, so there could be 100 milliwatt, 100 milliwatt, or say 120 milliwatt, something like that. So when you are working on a CPU, mainly it's ARM core CPUs, it could be quad core or it could be octa core. Uh, you may have 100 milliwatt targets or 60 milliwatt targets per core and etc. So that is your leakage power targets, and then now dynamic power. So how do you optimize your dynamic power when you are kind of implementing something that it is kind of say you're working on again uh, battery operated chip or devices, the chip that goes into battery operated, okay, more devices, right? So now how do you optimize your power? Dynamic power is also an important, right? So what are the different parameters that you consider? So that is why we have it like kind of your supply voltage, we try to bring it down, and then frequency is but we try to up frequency. They both are kind of interlinked. It's kind of when you increase the frequency, your power automatically goes up. So when you want power, you should and performance both. It is kind of chicken and egg problem kind of things, where when you increase your frequency, your power increases, and when you wanted to reduce your power, then you have to go and reduce your supply voltage, and when you reduce your supply voltage, your delay increases. So there are many things we would be talking in the upcoming classes. Okay, so this power topic is one of the important topic which you would be definitely need to know, so that there are different low power methodologies that we would be covering. uh, so how you can go and implement low power designs and etc., low power methodologies and all of that. Okay. Um, okay, so I think we will not be able to cover CMOS, the inverter operation. I think we have covered pretty much. So what we will do is we'll stop here for the day, and then we will cover it tomorrow. Complete CMOS circuits, inverter, AND gate, and OR gate, and NAND, NOR, and which is higher in terms of area. How do you design a circuit for a given Boolean equations and all of that tomorrow? Okay. I think that's all for the day. I'm done. And you have a question. I mean, if you have any questions, you can stay back and ask. If not, then you're free to drop. Okay, so Deves is asking, will that KMF based design implemented logic will reduce the switching activity here? So I think, see, ideally I won't be able to tell you because we are not doing any kind of optimizations manually, or what kind of designs that the other guys are bringing in, what kind of style the designers are following. So probably to understand that, we should actually talk to the designers, the RTL designers, and then understand when they wanted to drop, reduce the power, what are the strategies that they follow, and etc. So to answer your question, I'm not really sure because we use the tools, for example, like design compiler or genus and etc., to implement, to do the synthesis. So I'm not sure how, because that is internal algorithm which will not be known to outside world. So I'm not really sure. Okay, see you guys tomorrow same time. Bye.